Okay, last one. Yeah, so this brings it all together, and it's a good example actually. So a particle is moving in a straight line with acceleration at time t seconds given by a equals 2t minus 7. So we've got acceleration, almost certainly going to be some integration involved because we need to get probably back to velocity at some point, maybe even displacement. Okay, so expression for the velocity at time t seconds. So we get told the velocity is 10 at t is 0, so that's useful. We've got some initial conditions. So by integrating, v, velocity, is going to equal the integrated acceleration equation with respect to time. And so we get 2t takes 7. We integrate 2t takes 7 by adding 1 to the power, divided by the new power. Minus 7 will integrate to minus 7t easily enough. And we've got an add c here. So it's not definite integration yet. We need the add c. So we'd only be able to do any further work if we're only able to do any further work because we get told that t is 0 when v is 10. So we can use that to establish that c is 10 like so. So then we've got our, sorry about the mistakes, I did a mess up. I think I put a 3 here or something. Anyway, so velocity is t squared takes 7t at 10 meters per second. That's my expression for velocity at t seconds. Now the maximum speed, think about this, maximum speed occurs when when acceleration is 0. If we're interested in maximum displacement, that's going to be at velocity equals 0 or ds by dt equals 0. It's like a differentiation from before. A maximum value of y is going to be at dy by dx equals 0. Maximum value of v is going to be at dv by dt equals 0. I'm sorry, yeah. So I did jump B actually. I went to B. Yeah. So just looking at B first, then. Sorry. We've got to solve dv by dt equals 0, or that is to say, solving a equals 0. So the time at which the maximum occurs, the maximum speed occurs, okay, is at t equals 3.5. If we solve 2t takes 7 equals 0. And so, just like with differentiation, if the speed occurs at t equals 3.5, we can substitute that into our equation for velocity that we found in part A, like so. And we get a negative 2.25, so that's possible. We can have a negative velocity, but it wants the speed. So the speed is an amount, so the absolute value doesn't take into direction. So we've got 2.25 there. Going back to B, the times at which the particle is at instantaneous rest, or instantaneously at rest, well, instantaneously at rest, it mustn't be moving, so its velocity must be 0. So we just solve that velocity equation equal to 0. Okay, and that would be at t equals 2 and t equals 5. Incidentally, we could find its maximum displacement at these times, or maximum minimum. Finally, now this is pretty tough now. This is like what we had before. The distance travelled in the first 3 seconds. So on the face of that, you would be wanting to do, you'd be wanting to integrate velocity to get so that you're working with displacement, and it would be with limits 3 and 0. However, the graph for the velocity time graph for this is a quadratic, so it's this quadratic. In that interval between 0 and 3 seconds, we go above and below the axis. So to get the correct distance, okay, we're gonna have to, or the correct distance, we're gonna have to work out how much distance we have between 0 and 2 seconds, and using definite integration, as well as 3 and 2 to get that area as well. But that area is going to be negative. We're going to take the absolute value to get distance. So if it says here, we need to do integration on velocity with the limits 3 and 2 and 2 and 0, and add their absolute values for total distance. Okay, I hope that makes it makes sense why you need to do that for that. So it gets a bit small. I'll try and focus it. Okay, and then really it's just going to be a case of you copying that out. It's a bit of a lot. It's a bit of a lot. Yeah, so integrating the functions easy enough. It's just fiddly and a bit of a faff sorting the limits out. So we get to that. Remember, when we're doing definite integration, the plus c's cancel, so we never have to worry about that for definite integrals. So we've got, when we substitute a 3 in then and 2, we get negative 7 over 6. So that area is negative 7 over 6. Well, the area is 7 over 6, but the displacement would be minus 7 over 6, but we need the absolute value. So we'll leave that there. And then we've got t, I didn't write it out because I ran out of space, but you would be expected to write out the substitution as well. We're going to substitute 2 and 0 into this now, and you get an area between 0 and 2 of 26 over 3. So the total distance is 26 over 3. That's distance travelled in the first 2 seconds. Add 7 over 6. That's distance. It doesn't matter about the negative because it's distance. That's distance travelled between 2 and 3 seconds, giving me 59 over 6 metres in total. Right, that will do it. Do your homework, do those notes, and Friday I'll set you some work based on this. I mean, if you really want, you can look in the textbook, there's stuff in there. But I'll set it on Friday. Okay, hope you're all well. Cheers.